1,000 years ago, religion and chemistry seemed one and the same. A holy man's first duty was to heaven, life after death. But some were tempted by alchemy, the idea that chemical spells might somehow make a man live forever. Monks were among the first to try to identify chemical elements. The simplest substances must be closer to God, they thought. But then many materials seemed charged with supernatural power. Materials like this strange red earth from Spain, called cinnabar.
Now the substance of cinnabar is such that the more it is heated, the more exquisite are its sublimations. Cinnabar will become mercury, and passing through a series of other sublimations, it is again turned into cinnabar, and thus it enables man to enjoy eternal life.
Silvery metal mercury, conjured by fire from red earth. It looked like witchcraft. It seemed that God had left clues planted in nature for alchemists to discover. Crack those clues and you might gain supernatural power. This green rock was just such a clue. Roasted in a fire, it dripped liquid copper. Why? How did the fire set the copper free? What exactly was fire? A new word came into the language, reduction. It meant to simmer out basic substances by fire, to reduce complex compounds to simple metals. Hundreds of years passed before people realized that all this was not magic. It was chemistry. Fire, too. Fire is just a chemical reaction with oxygen, an oxidation reaction. Now we know that oxidation and reduction are flip sides of the same chemical trick. But the alchemists were right about one thing. Chemistry has brought the power to create our own future, even to bring the past back to life. It looked like the perfect spot to build a dream home, at the edge of a pretty village in the west of England. But when Jill Bushnell's husband started digging the foundations for their bungalow, this is what he found. Time to call in the professionals. The police weren't interested. This was a case for the archaeologists. Soon they were crawling all over Jill's garden, recording everything they found scientifically.
It is somebody who's buried here, and I visualise that they lived probably further down the village, and they decided that this was a special place to bury their dead, and so therefore we have to treat it with respect.
Who were these people? 1,500 years ago, our ancestors lived and died without many answers. They did know that nothing lasts forever, but they can't have known that chemistry is the reason why. Today we know that bodies rot in a soup of complex chemistry. Oxidation plays a big part. But the good news for archaeologists is that sometimes it takes a very long time. In Jill 5 bodies, 6 in all. There wasn't much left of the bodies themselves, but next to one of them was this vital clue. It's a Saxon sword made of iron. More than 1,000 years of rust has turned most of it into a form of iron oxide. Rust is the biggest enemy for professional conservators like Lynn Wotton.
The Saxon sword came from a site just outside Salisbury. It was a chance find. Somebody found it in their garden. It didn't come into a museum for a number of years, and it hasn't been treated. The whole of the surface is coming off. And we've lost part of the edge there too. The sword has classic iron corrosion flakes falling off the surface in layers.
Corrosion is caused by oxidation. Somehow Lynn has to stop it, or another piece of the past will just rust away. Trouble is, the air around us is about 1/5 oxygen, and it's hungry for metals like iron. Dissolved in rainwater, oxygen will even find iron buried deep under the ground. That's how rusting starts. It's easy to show this happening. If you boil water, dissolved gases like oxygen come out with the bubbles. So in theory, boiled water should cause less rusting than water straight from the tap. Time for an experiment. This is wire wool. It's made of iron, just like the sword. The water in this jar has been boiled, so it shouldn't contain much oxygen. But the water in this one is straight out of the tap. An hour later, the iron in the jar with the boiled water hasn't changed. But the rusty red of iron oxide is clear in this jar. Dissolved oxygen has combined with the iron, so we say it's been oxidized. That's true, but it's only one way of looking at it. Look much closer, and you realize that oxidation doesn't center on the oxygen at all. Oxidation is really all about the movement of electrons. This represents the surface of a piece of iron. The iron atoms are organized in a regular pattern called a lattice. Between the atoms, a sea of negatively charged electrons flows freely. When the iron meets water containing oxygen, the conditions are ripe for rusting to take place, because the water and the oxygen together attack the iron. Electrons leave the iron and move towards the oxygen, leaving the iron positively charged. With the help of the water, the oxygen molecules split up and absorb the negative electrons from the iron. They become negatively charged themselves. Remember, the iron is positive, so the opposite charges are attracted to each other and combine to form rust. The iron has combined with oxygen, but it's lost electrons. Here's one way to remember that. Oxidation is loss of electrons. Reduction is the exact opposite. About the time that the word reduction was invented, vast cathedrals were being built right across Europe. Very few people could read or write, so stories passed down the generations through pictures and preaching. Master glassmakers were in demand. Like the alchemists, glassmakers kept their discoveries secret. That way, no one could steal their power or undercut their prices. The biggest secret of all was how to put bright colours into glass. But in 1140, a monk in Germany decided to tell the world how it was done. Theophilus Presbyter wrote down all he knew about glassmaking. Not just clear glass, but coloured glass too. Furious glassmakers raided medieval libraries, ripping out the pages that gave their secrets away. Every surviving copy of Presbyter's book has chapters 6 to 11 missing. But you can't hide the truth forever. Today we know that clear glass is an oxide of silicon. To colour it, you add traces of metal. Then you fine-tune the colour using oxidation and reduction. Modern glassmakers, like Sidney Langley, still need the mystery of art for their work, but they need science too.
It's very exciting when you come up with a new design, and it's very often travel that does this for me. I did a day trip to Marrakesh and was really inspired by the Islamic architecture that I saw there, and this is the design that's come out of that. This is a colour I use a lot.
The silvery pattern really is silver, a kind of silver oxide. There's a treasure trove at the bottom of Sidney's garden, her workshop. The first step is to choose the right raw materials. She starts with lumps of clear glass called cullet. Before she melts and works on them, she sometimes adds a colour.
There's lots of different materials go into the colours. In a blue like this, you'll have cobalt. The green will have copper in it. And copper also makes a wonderful sparkly glass called copper aventurine, where there are copper crystals suspended in the glass.
Bringing out that sparkle is what glassmaking's all about. Heat from this furnace will trigger a whole chain of chemical reactions. The hot glass cools rapidly, so Siddy must be quick rolling metal oxide into the surface. Damp newspaper starts to reduce that oxide to metal. Everything Siddy does starts another chemical reaction. Oxygen from the air and Siddy's breath will reoxidize the surfaces, inside and out. It might not look like a science lab, but there's a lot of chemistry going on here. Science gets Siddy started, but here's where the art comes in. Now she's blown the glass to size, she can set to work shaping it.
When this piece is finished, it's going to be an oval cross-section vase with an uneven, rather organic rim to it. I'm just opening it out with the wooden jacks here.
Almost done. At last, the silver colour has come out. Siddy rolled on dull metal oxide, but she's transformed it into a thin layer that will never lose its shine. To see how, here's an experiment with another shiny metal, lead. The black powder is carbon, and the light-coloured powder is lead oxide. The lead is locked into the lead oxide, and heat alone won't split them apart. But add carbon, and that changes everything. As the mixture gets hot, 2 lead oxide particles react with 1 carbon atom. Oxygen leaves the lead oxide and transfers to the carbon. That makes carbon dioxide gas. It's invisible and just escapes into the air. But these tiny drops of lead get left behind. They've lost the oxygen they were paired with. So one way of understanding reduction is to say that it's loss of oxygen. But there's another way of looking at reduction, as a movement of electrons. The reason that lead and oxygen stick together in lead oxide is because they have opposite electric charges. The lead ions are positively charged and the oxygen ions are negative. Lead oxide is an ionic compound. But carbon doesn't like to form ionic bonds. Carbon and oxygen will only join together to make carbon dioxide with covalent bonds. So before the oxygen can join with the carbon, it has to get rid of its extra negative charge. The oxygen must give electrons to the lead. The lead ions gain electrons. That neutralizes their charge and turns them into lead atoms. It turns out that whenever something gets reduced, it gains electrons. So chemists actually define reduction that way. They say, if oxidation is loss, reduction is gain of electrons. Legends about science might seem to belong to the past, but even now, when we've explained so much, there's still something magic about chemistry. So maybe it should be no surprise that new myths have sprung up about one reaction in particular. Search on the internet for the word thermit, and you will find hundreds of pages. Hans Goldschmidt discovered the thermit reaction in 1895. It was so violent that it was used in wartime to make fire bombs that could set cities ablaze. But in peacetime, many people have also tried to harness its power. A story has spread round the internet about the thermit reaction and this river, the St. Lawrence River. It runs down from Canada and on to the east coast of America. For a long time it's been an important route for boats carrying cargo inland, through the small town of Waddington, USA. Most winters last century the river froze, sometimes for weeks. It took icebreakers to cut a path so boats could get through. But legend has it that on February the 24th, 1925, someone set off a massive thermit reaction on the ice near Waddington. A reaction so big that it cut a path through 250,000 tons of ice. Could that really be true? Short Circuit took great care when we set up this demonstration. The grey powder is aluminium. The rusty red powder is iron oxide. We put the mixture into a ceramic pot to withstand the intense heat. A thin strip of magnesium acts as a fuse. The reaction is highly exothermic. It clearly releases a huge amount of heat. What you can't see is why. What's happening inside the reaction. At room temperature, aluminium and iron oxide don't react. It takes the heat from something like burning magnesium to get them going. After that, the magnesium isn't really part of the show. The fireworks happen through this reaction, because aluminium and oxygen are both such reactive elements, and they're desperate to get together. Metal aluminium goes in, and it comes out oxidized. But the iron oxide that goes in comes out reduced. You could say that the oxygen has swapped partners. It's gone off with the aluminium and dumped the iron. Here's the proof. At the bottom of the ceramic pot we made a hole, so whatever is left behind by the thermit reaction would drip down into this sand-filled bucket. It's iron metal. Because the thermit reaction combines both reduction and oxidation, it's called a redox reaction. All this from a cup full of chemicals. What would happen if you did it on a much bigger scale? Could you really melt 250,000 tons of ice? 3/4 of a century on, no one can actually find proof that the St. Lawrence River was melted using a thermit reaction. But thanks to the internet, a new legend has travelled all round the world. True or false, it keeps Waddington on the map. And it proves people will always look for miracles in chemistry.